Welcome to Walkabout the Galaxy, the barely astronomical astronomy podcast.
Oh my.
Where the science is universal, the opinions are personal, and the sponsor is biological.
Okay.
We are Strange, Charm, and Top the Astroquarks, also known as Josh Caldwell, Addie Dove, and Jim Cooney, coming to you from the Walkabout Studios at the University of Central Florida. Jim, fission or fusion? Switch things up a little bit there.
I thought it was going to be about fishing.
Maybe it was.
Maybe it was. Yeah, he slurred it just enough that...
Just enough.
He hasn't even had any sangria.
Fission or fusion. There are many multiple... You can choose your meaning of any of those words.
Oh, wow.
Asian cuisine,
So choose your
on the
own
one
adventure.
hand.
That's true.
Nuclear reactions.
Yeah.
Sitting on a boat.
Well, fission is great, but fusion is even better.
Oh.
Like fusion.
I like fusion. Well, partly because it goes with the
Stars do
theme
it.
of our discussions today. We're going to talk a little bit about neutrinos,
alert.
and one of the products of a fusion reaction is...
Neutrinos.
Neutrinos.
Not a product of a fission reaction? It is,
I don't know.
isn't it? Maybe not.
Maybe.
Neutrons are.
Yeah, neutrons, but
Yeah.
not neutrinos.
Yeah.
So-
You know what they say?
No.
You teach somebody to fish. No, what do they say? Give a
Definitely that.
person a fish, they have a nice meal.
Yeah.
Teach a person to fish, they waste all day sitting in a boat.
Oh, no.
They don't say that?
No.
Say that?
Okay.
Not in my house.
Not my house.
Addie, this one's an easy one for you.
Okay.
Q-Pace or SurfSat?
Surfsat! Yay!
Hey.
What are these things?
These are CubeSats, which are tiny little spacecraft,
you
the size of a Kleenex box.
UCF's first two CubeSats.
Yay!
Excellent.
Yeah.
And you guys are the PIs for these.
PIs.
So, right.
I like CubePace, but I am the PI of Surfsat. It's my baby.
Yeah.
Right.
That's her baby. I saw it. It's a beautiful little it's a
she's-
beautiful little satellite.
It's
Yeah.
pretty crazy.
It's very cute.
She's pretty cute.
Has solar
She's
panels.
got some brains
has some-
now.
There's some green on the outside. Is like some green and some white and some black and some other things going on. There's some
Pretty cool. Some
guitar
orange and yellow.
strings.
Yeah.
Right.
When her little antennas deploy, it's so
And
cute.
there's-
She's got these little antennas that stick
Aw.
out of her head.
yeah, guitar strings and fishing lines.
Yep.
Why is it
Why?
female?
It just is.
Fair enough.
Yeah.
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 Why not?
Like ships. Yeah.
Yeah, exactly. A lot of spacecraft are given spaceships are given female names.
Okay.
Spacecraft are not
female-
always, but
they're given-
spaceships often are.
Like what?
Or often
I
referred
mean, they're
to,
given the female pronoun,
I guess,
but
yeah.
not
Maybe that's
necessarily
just 'cause
female
it's always-
names.
Yeah.
Why is it with ships?
I don't know.
Yeah.
I don't know. Some historic
Enterprise.
thing. I don't know why.
She's a beauty.
Yeah.
But you don't say name my daughter Enterprise. Not,
That'd be.
not yet.
I was gonna say, yeah.
Your next
That'd be
one.
totally
named-
normal in today's
did-
children naming culture.
Yeah.
Yes. Well, my daughter, as you know, does have a Star
true.
Trek name.
What?
Yes.
Yeah.
Awesome.
Not Enterprise.
No.
Today we're going to talk about a neutrino observatory, as you mentioned, in the mysteries of neutrinos and active galactic nuclei and supermassive things, which we love to talk about. Neutrinos, cosmic rays, which I think are two of the coolest sounding particles in astrophysics.
Sure.
What
they
about
both sound made up.
what about
Cosmic
what
ray
about
sounds.
quarks?
Quarks are cool, but they also sound made up. They sound goofier than cool.
We do sound pretty goofy, also.
Cosmic ray sounds like something from a Flash Gordon thing.
Yeah.
Like,
Yeah.
I'm going to get my cosmic ray gun.
I think there were cosmic ray guns, probably.
There may well have been.
Oh.
Yeah.
And neutrinos sounds a little bit on the quark side of the silliness spectrum. Yeah. But first, speaking of silly,
Yes.
this episode of Walkabout the Galaxy is brought to you by...
Jim's shirt. No, I actually really like Jim's shirt. I was just noticing it. It's a good Hawaiian print.
Yeah, it's not
not
too
silly, actually, at
Cool
all.
guy today.
I
Yeah.
was just looking at it.
Yeah.
Sorry, sponsor. Continue.
If only that were our sponsor.
That'd be pretty great. Next time.
In fact, this episode of Walkabout the Galaxy is brought to you by Odd Bodily Secretions.
Oh,
Oh, no.
that's less nice than Jim's shirt.
Step aside, pee, poo, and snot. You've had your time in the limelight. Don't let the cutesy names of sleep, earwax, belly button lint, and toe jam deceive you. What's the difference between the gunk in the corner of your eye and a good old-fashioned nose booger anyway? Ever wonder what earwax is? 'Cause it sure ain't wax. While you're pondering the mysteries of the universe with the Astroquarks, here's a question more mystifying and profound than multiverses and quantum physics. Would you rather put an eye booger in your ear or earwax in your nose? Odd bodily secretions for the real big puzzles in life.
Interesting.
I'm not sure we should have accepted that.
We branched out a little bit with our sponsor today.
Yeah, we sure did.
Well, we have a broad reach.
We do. And you know what? Bodily secretions are made up of quarks and other types of particles.
Ultimately. Yes. Well, I mean, when the sponsor message came in, I had the same reaction. I thought, that's weird.
Yeah.
And then I was like, well, Star Trek was probably sponsored by Lysol. And what does Lysol have to do with exploring the galaxy?
Well, you got to keep those germs. It's a whole contamination thing.
Yeah, I think
Yeah, the planetary protection people just thought of Lysol.
I wonder.
Joking,
yeah,
mostly.
What do they use?
They just don't send things places.
We do send things places. We send things to Mars.
Yeah. How do they?
What do they do?
Do they irradiate it or something?
So there's some irradiation, but usually you just use alcohols.
It's really hard to kill bacteria.
Yeah. You're never going to get it all. I mean,
no, there's definitely bacteria we sent to Mars and the moon.
Absolutely.
Yeah.
Like if we find life on Mars, it maybe is because we put it there.
Yeah. We just invaded Mars.
Oh man.
Yeah.
Mars attacks.
Yeah. Any nerd news?
Ant-Man and Wasp came out, but I haven't seen it.
You've been too busy surf satting.
Too busy surf setting.
Yeah.
I still haven't seen Infinity War.
That's how
surf setting.
you're losing your nerd cred.
I know.
Yeah. That you're going to have to see that on an airplane.
Oh no. It's not good on an airplane.
Right. On the smallest screen possible instead of the
I'll
largest
just
screen
watch it at your
possible.
house on your new big
There
screen.
you go. Yeah.
I did on not really nerd news,
Oh.
but I did this weekend get a chance to kind of play
That is
yeah.
nerd news.
the national
It's a different
champion
kind of nerd.
of
You played the
Scrabble.
So you
national
did
champion
play
of
the
Scrabble?
national champion.
Yes and no.
Oh.
So he was not playing. I played in a Scrabble tournament this weekend. The national champion was not playing in that tournament, but
Wait a
after
minute,
the tournament,
The guy was there, but he wasn't playing in the tournament?
after the tournament, we were up in Jacksonville and we went to a Jacksonville Jumbo Shrimp game. And I'm going
that's
to give
not a
props
thing.
to the Jacksonville
Very
Jumbo
sorry.
Shrimp. They're a
Is that
double
like a double A
A
baseball
major
team?
league, double A baseball team, minor league baseball.
I didn't know about them.
They just changed it. They used to be the Jacksonville Suns. Now they're Jacksonville Jumbo Shrimp's awesome. Their mascot is Scampy. Is his name? It's a little shrimp-looking thing running around. Anyway, it was great. But during the game, the national Scrabble champion was there and set the record, the Guinness Book of World Record for most simultaneous games of Scrabble played.
Okay.
And so
and what is the record?
it was only 30.
And was there a Guinness,
I don't know if there was a previous record or not.
Was there a Guinness rep there to certify this record?
Not that I'm aware of.
But it was documented, and
I think it was documented. Yeah, I mean they
Things
were
will be
they were
sent.
attempting to do it legitly.
Okay.
Yeah,
Exciting.
and I
don't
was one of
think-
the players. And we didn't actually finish the game. So he's basically there was all of us lined up, and he was just going from one to the other, spending 5 seconds and making a play, and then moving on. So we got through like 4 or 5 turns, but after those 4 or 5 turns, I was beating the national Scrabble champion.
Wait a minute.
Now that's largely because he was spending 5 seconds making a play while I was sitting there for 10 minutes.
He's planning to get a world record for playing 30 games of Scrabble simultaneously, but only played 4 turns of each game.
Something like that. I don't know. I think that, who knows? Maybe it won't be certified or something, but he was playing all those games.
I could do that. I mean, I can get 30. I go buy 31 Scrabble boards. I go out there and play 4 turns of Scrabble.
It's a big commitment.
You could.
31 times.
You could.
Yeah.
You could do it.
What's
Any of these things. I mean, this wasn't not a particularly impressive Guinness record, but it's just a thing.
Yeah, I have to say I'm not.
It was like a.
Ouch.
But it was cool to meet and talk with the national
Did
Scrabble
he use
champion.
lots of big words?
Yeah.
Lots of 7-letter words?
Yeah, many 7-letter words were used over the weekend.
Did he use any J and Q or V words?
I don't know.
I
can't
decided
remember.
V is my least favorite Scrabble.
Oh, it's
letter.
very difficult.
Oh,
It's a
no,
terrible
really?
Scrabble tile because no 2-letter words have V in it, and so it's very hard to overlap
Really?
things.
Yeah.
My favorite incident for the weekend was we had one of the players. I was watching the game, and he had his like 8-year-old son there was watching the game, and his opponent played shitter. Right in front. It was pretty fun.
Nice.
So it's got unfortunately, in tournament Scrabble, all of the bad words, racial slurs, and
geez.
graphic things are all allowed, and people will play them without a second thought.
It's just a word.
It's a word. Yeah, they're all just.
They're all just tiles.
Yep.
Yeah, that's not a particularly high scoring word unless you got some.
No,
wolf
well,
players.
it was. That's a bingo. It uses all 7 letters. So.
Yeah.
I think that's called a Yahtzee.
Right.
Okay.
Sorry, Jim.
All right. Onward. I apologize.
Speaking of Yahtzee.
Uh-huh.
Ooh, that's a good game.
Neutrinos.
Neutrinos.
Yeah.
Very similar.
So there was a discovery announced this week, some papers that were published by the Ice Cube Consortium, which is a bunch of rappers.
Is that different than the Ice Tea Consortium?
Yeah, no, this is all a bunch of rappers.
Okay.
Yeah.
Mm-hmm.
No, the Ice Cube is a neutrino observatory.
Oh, okay.
That makes sense. Makes
more
sense now.
Yeah.
All makes a lot of
Before
sense.
I was really
Still
confused.
doesn't make any sense yet, Ed.
Okay. That's why we're going to talk about it.
Yeah. The Ice Cube Observatory is down under. Way down under.
Way down under.
Australia.
No, further.
No?
Further down. Yeah.
Yes, yeah, it's at the South Pole Station.
Oh, that makes sense. There's a lot of ice there.
Yeah.
Yeah. And I love the observatory, the part that least is above ground, totally looks like something from some movie. Like from John Carpenter's The Thing, or some movie where aliens invade and, you know, it's some remote outpost at the South Pole discovers it. It's very, at least in low res, which is what I'm looking at. In low res, it looks very cool. Maybe if in detail, it would just look like some shack. But yeah, probably not.
Yeah, I don't know. But
construction costs are high at the South Pole.
Yeah, yes, this really is literally very close to the actual geographic South Pole. There's of course, there's a whole station down there with, you know, a few hundred people all the time that they run a lot of astrophysics experiments down at the South Pole.
What's so special about the South Pole?
So
physically speaking,
many things are special. For the South Pole, for many of the astrophysics things, it's special. Well, because if you're at the South Pole, you're always staring at the same splotch of sky, right? So if you're on the equator,
I'm looking around.
Right, but if you look directly up from the South Pole, you're looking at the South Celestial Pole. You're looking at, you know, a particular splotch of sky, and you can basically keep your telescope pointed at that same splotch of sky for 6 months consecutively until the sun comes up. And if you're not looking in visible light, you can just do it
all
the time.
Yeah, but the South Celestial Pole, that's 1 point.
Right. So if you're only interested in looking at something that's there, then you're in good shape because you can look at it all the time, and the weather is generally great.
Right.
Astronomically speaking.
Cold.
Yeah. It's ridiculously cold, but I think the record high at the South Pole Station is something like 9.9 degrees Fahrenheit minus.
So much for global warming.
Yeah. But it's very dry there.
Actually, it's
the
been a big
altitude is high.
For researchers going down to Antarctica, because you are leaving. They usually leave from Australia or New Zealand, and they go to McMurdo, but the ice has been melting, and they haven't been able to land and get people in and out sometimes last season.
Because they land on skis basically.
I think so,
Yeah.
But I'm still I'm still not sold on the South Pole aspect of things. So,
it's high altitude. It's dry.
But that's kind of true for a lot of places.
It's true for a lot of
Antarctica.
places.
And the main bases that Addie was just mentioning, McMurdo, is not at the South Pole.
Right.
You know, it's a somewhat easier place to access.
Yeah.
And for this particular observatory, it doesn't particularly even care about direction, does it?
No, this one does not. So this is an awesome observatory. It's not like a typical telescope. It's basically 1 cubic kilometer of ice, where they've set up a bunch of these, light sensors.
So it's an ice cube.
It is an ice cube.
Interesting.
It's
awesome. It's really remarkable. I mean, the whole thing, and of course the reason they go down to, I don't really know why it's at the South Pole directly. But the reason why they go down to Antarctica is because you want a large amount of ice that is very pure, right? So pure so that it's clear.
Because the ice is the detector.
The ice is the detector, right? The idea is neutrinos are ridiculously difficult to detect.
It's somewhat part of the detector. I guess it's a step in
right,
the detection
right. So
process.
it's the substance which the neutrinos interact with, hopefully, right? So if you have enough neutrinos flying through this big cubic kilometer of ice, a handful of them will interact with a nuclei in the
actually not the molecule, but with a nucleus
with a nuclear particle in the ice. And that produces a little bit of a light show. And then you have a bunch of light detectors and you see that, but
a light show.
You need something very clear in order to see the light, from the interaction. So you need either water or ice, but it needs to be ridiculously pure without, little
cracks,
air bubbles and various things like that. And the best place for that is Antarctica because it's got this ice sheet that has been slowly compressed over a very long period of time and is, in addition, you need it shielded from radiation in the Earth's atmosphere and things like that. And so it's like this cube starts 1,500 meters below the surface. Whoa. And then extends, another 1,000 meters down, and so it's protected by a kilometer and a half of ice above it.
So it's interesting, right? Because it's using two different properties. Because ice and water are really good for shielding certain energies,
right?
So like a lot of times when we talk about a spacecraft, one of the best ways to like protect astronauts is to just make the walls all have water in them, right? It's the most effective.
They're very
shielding.
good for like absorbing neutrons, which is a dangerous to humans kind of radiation that comes from other processes, the neutrinos.
But the neutrinos can go through like anything.
Yeah, neutrinos go through lots of stuff.
They're going through you right now.
Yeah. That was one. We have two trivia questions today, and one of them has to do with that, so we won't go too far into how far neutrinos penetrate.
But I want it, so the neutrino comes in and it interacts with it. Is it with the proton at the nucleus of the hydrogen atom, or is it with the nucleus of the oxygen atom?
It may be any of the nuclear particles.
But it's got a greater probability, I think, of interacting with the hydrogen, with the proton, doesn't it?
It could. I don't know.
Okay.
Yes, definitely.
Hey, if you say so.
We don't know. I'm not saying so. I was asking so.
Yeah. Oh, I don't know the answer to that.
Right.
But
so it interacts and it produces a light show. And you said light show, I think, in the somewhat figurative, poetic, hyperbolic, even perhaps, use of the term. How many photons are produced by this interaction of a neutrino?
Yeah, not many, like a couple.
Okay. And those go off in a direction.
Right.
So then you actually have to have your real detector on the edge of this ice cube to pick up that photon.
Right.
And so is the entire cube surrounded by light detectors?
So it's surrounded by light detectors. I don't know how many there are exactly. I don't know if every possible photon that could escape from that would get picked up. Probably not.
Yeah.
But
so they dug or bored holes.
Right.
1.5 to 2.5 kilometers down into the ice.
Right.
And placed 1,000-meter high columns or arrays of light detectors all around this cubic space.
Yep.
How about the bottom or the top?
I think they're on the bottom and top as well. I mean, I don't know how they did that. The engineering feat seems impressive. But, and of course, then you have all kind of problems, like if one breaks, what do? You can't get to it if they're frozen into the ice once they're there.
And the neutrinos themselves just pass right through those light detectors. They don't care at all about those. In fact, the vast majority of them, maybe this gets to your trivia question, pass right through the ice as well.
That's right. Only a tiny fraction
of them will do something, produce a photon, the thing picks it up. So, and what's the discovery?
So the discovery, so we've had neutrino detectors for a while.
Neutrinos.
The vast majority of the neutrinos that they detect are neutrinos from
the sun.
Right.
Yay.
So the sun is as we said at the beginning, the sun is a big giant fusion reactor in its core. And fusion of hydrogen into helium. One of the products of that reaction is neutrinos. And so most of the neutrinos that are passing through us right now are solar neutrinos. But
do we have a neutrino problem?
A neutrino problem. We used to have a neutrino problem.
There was a neutrino problem.
There was a neutrino problem.
There's a famous factor of 3.
Yeah, we predicted we would see X neutrinos coming, per second from the sun, and we saw X over 3 coming from the sun. And that had to do with the fact that neutrinos famously just switch their type in mid-flight.
So we have 6 quarks, 6 types of quark, and there are how many types of?
There are 3 types of neutrinos.
Maybe we should have been the astroneutrinos.
It doesn't ring quite
roll off the
well,
tongue
though.
quite as well.
We got 3 types of neutrinos, and we can only detect easily one of them.
Which is the tau?
Which is the electron neutrino.
That's what I was going to say.
That's not what you actually said.
No, but that's what I was going to say.
But it turns out that they can switch flavors of these 3 neutrinos mid-flight. And so we originally referred to that as the solar neutrino problem because we were only detecting a third of what we saw. But that was...
And also, that was the fact that they could change flavor. Wasn't that a big part of discovering that neutrinos actually do have some rest mass?
Right, yes.
This was another big neutrino
which we still
mystery.
haven't measured what that mass is, but we've measured the difference between the 3 flavors of things. They each have a slightly different mass, and we know what those differences are between the 3 masses, but not what the actual mass is.
So neutrinos, for a time, when I was a youngster, was hypothesized maybe they had no mass, like light, and traveled at the speed of light.
Right.
Now we know that they do have mass. We don't know what it is, apparently.
No.
But, and that, because they do have mass, they don't actually travel at the speed of light.
Right.
Just under.
Just under.
Yeah, I mean, we've constrained the mass of it. It's definitely less than about a millionth of the mass of an electron. Yeah, they are. Anyway, back to what this detection was. So most of our neutrinos come from the sun, but some neutrinos come from deeper in space, cosmic neutrinos.
Other suns.
And we've been wondering for a very long time where those very high energy neutrinos that are coming from out in the universe, where they're actually coming from.
How do we know how high energy they are?
Well,
aren't they all kind of the same?
I mean, no. I mean, neutrinos, just like an electron or something like that, the faster it's going.
They're not all traveling at the same speed?
No, they're not all traveling at the same speed.
Oh.
No, it doesn't have it's just like any other particle that can have any energy it wants. And so these guys have very, very high energies, these things that are coming from deep space.
But can we detect, so with the ice cube detector, can it tell the difference between those energies?
Yes,
Wow.
because the energy of the products of the reaction are going to be
different.
The products of the are going to be different. So
Okay, so you're going to get higher energy photons. coming
higher
out.
energy things coming out of that thing. It's not immedely photons. There's muons. There's all these other things involved in this. But they are very smart folks and
It's
can
too
figure out.
complicated.
They can figure out what the result is. And these things, because they come in from a certain direction, the products end up coming out in certain preferred directions, and so they can narrow down the direction in the sky that these things come from. Not exactly, but within, half a degree or a tenth of a degree or something like that in the sky.
And ta-da.
And so the big thing that they discussed that they talked about last week was they'd found one of these neutrinos, single detection, coming from a spot in the sky that at the same time we saw a big gamma ray burst coming from. And we're able to detect what the source of that was. It was this thing called a blazar.
Blazar.
That's pretty awesome, right?
That's a good made-up
cool
sounding
name.
word,
That
too.
is a very
Yeah.
good name.
Good Scrabble word.
It wouldn't have been exactly at the same time since the gamma rays are traveling at the speed of light.
Right, gamma rays are traveling.
The
So
neutrinos are getting there a little bit later.
when I say the same time, this was not an event that was very localized in time. It was just there was a weeks long increase in the gamma ray, gamma rays coming from this
Okay.
blazar, and roughly coincidentally, this neutrino.
So now we have a source for
Right.
some extragalactic neutrinos.
Right, and it's cool because that's the first time we've kind of definitively, I won't say definitively, but fairly definitively found a source for one of these really high energy neutrinos
From outside
of our solar system, and that's cool because it's a little bit like the whole gravitational wave thing
I was
was
just
awesome
about to say that, yeah.
because it's like astronomy in a regime that's not light. Right.
Yeah,
and so,
yeah.
doing
And it's these
neutrino
detectors.
astronomy is kind of another way to do astronomy. And if we can regularly figure out how this works, it's going to be kind of awesome.
Yeah.
Another
And there's
window
been
into the universe.
neutrino detectors for a while, right? People
Yeah.
have like pools of water and things like that.
Yeah.
But just like how we have had thought of ways to detect gravitational waves before, it's cool to actually have the sensitivity and the resolution that you need
Right.
to be able to detect these
to
now.
actually detect them. So,
All right.
kind of
So
awesome.
before we say what a blazar is, let's hear your trivia.
Okay.
Okay. Well, there are two trivia.
Okay.
So much trivia. All right. But the trivia that we're just referring to, and then I'll do the other trivia. So neutrinos, as we discussed, they're tiny, not very interactive particles.
Kind of.
So
like
what I
some
want to
people
know
we know.
is from
Jim's
you guys.
holding his fingers
They're
together.
really
very,
close.
very
Really close.
It's like
less than an
smaller-
inch.
Yeah, less than an inch.
So I don't know. What is the mean free path? Which you guys know what it is. For some of the listeners who might not, that's the average distance that one neutrino would travel before having an interaction with something.
With anything.
With anything.
Okay.
So what is the mean free path, the average distance a neutrino of a neutrino going through ice? So if you had a block of ice, how big, how long, and a neutrino is going through it, how big would the block of ice have to be in order for the neutrino to interact once on average?
Can I give my answer in units of the Titanic?
You cannot. I will give you multiple choice possibilities.
Oh, great.
Yes.
Good.
Are they in Titanic units?
Can you convert
Meaning the
those to-
length of the boat, the Titanic?
Yes.
Oh,
Can
that's.
you, can you convert it to Titanics?
Trying to tie ships back in now.
I guess we could. That would take a little while.
Okay.
Your
How
choices
many
are
cube
A,
sets is it?
10 meters, B, 10 kilometers, C, 10 Earth radii, D, 10 AU, or E, 10 light years.
What about?
I'm going to go with 10.
Are we answering right now?
No, but we'll
No.
come back.
No, think about that. All right.
Okay, but there's two trivia
The
questions.
second
Are
trivia
they
question. Just
linked?
think about that one. That one's kind of a
about
technical-ish one.
Okay.
Which again, that's kind of like you know it or you don't. I don't know. But
You could,
here's the
you
other
could
one.
suss it out.
You could,
could
you
logic
can
it
guess
out.
it.
yeah.
Or, yeah.
Which of the following fun astronomy physics things had the shortest time elapsed between the prediction of their existence and the confirmation of such?
Okay.
I know the answer before you even give the choices.
Gasp.
I picked 5 things. Okay, one, A.
They're all wrong.
The neutrino.
Well, I hope one of them's right.
One of them is the shortest of his list.
The shortest of my list, right?
But I bet he doesn't have the shortest that there was.
Probably not.
Oh.
Definitely not.
Oh, this is going to be some sort of
I just
Cassini
randomly
reference.
picked 5 cool
Okay.
physics astronomy things.
Go ahead.
A, the neutrino, because that's what we've been discussing. B, gravitational waves. C, the Kuiper belt, which we discussed last time. D, the truth quark, top quark, me. Or E.
Oh, doing a name change.
I think I might do a name change. I think truth quark is cooler than top quark, and I wish I'd thought of that at the beginning. Or E, my wife's bottom quark, or beauty quark.
Okay, so and we're looking for the
shortest time
between prediction and discovery.
Between prediction by some scientific model and its discovery.
What about shortest time?
Neutrino, gravitational waves, Kuiper belt, truth quark, bottom quark.
Can I give my answer to the trivia questions in terms of shortest time divided by distance from mean free path?
No.
Okay.
Oh yeah, we should do the velocity of the answers.
The velocity of the answer. Yeah,
Yes.
exactly.
3 Titanics per
No, that's a distance.
per
Okay. Yeah.
fortnight.
I've heard that's a fun game.
Fortnight.
Lots
Oh
of kids
yeah.
are playing it these days. Okay, we don't answer right now.
Okay.
All right, mull that over, guys.
Blazars.
Everybody mull it over.
Yeah. Okay.
How bizarre. How
How
bizarre.
bizarre.
So what is a blazar anyway?
It's a very tacky sports coat.
Yeah. There's so many good puns for this one.
Yeah. A blazar is a quasar.
Is a quasar?
It is a quasar that you're looking
By
down the
any other
barrel
name.
of.
Right.
Yeah.
Quasar by any other
So
name.
these things, lots of fun.
I will say I did love, there was one of the articles we looked at about this had this really awesome artist depiction of a quasar.
Yeah.
And it just looks very interstellar.
A blaze
Yeah,
of quasar.
that's today's, the day we're recording this, today's astronomy picture of the day is that.
It is?
It's an artist's rendition of what the
Okay.
core
If
of a
you're not
blazar.
familiar with
We'll put a link up
APOD,
to
it's a
it.
pretty great website. It's a great homepage.
For sure.
Astronomy
Absolutely.
picture
I
of
look
the
at that
day.
every day.
Yeah.
Nerd.
One of the
I might
things
be a
you'll
nerd.
see a lot in science fiction and sometimes in actual photographs of things in the universe is a disc-like thing with
A jet.
a jet coming out perpendicular to the disc.
Yeah.
Right?
Yeah.
Usually
And
at the center.
yes, at the center of that disc, a jet going up and a jet going down, if you can see them
If you can see both sides.
Yeah. And basically when things are falling in towards the center, instead of falling in spherically, interactions between all those particles falling in tend to make them end up in a disk, which why all our planets are kind of in a disk and so on. The universe loves disks.
Yeah.
It's true.
And so when that stuff's coming in,
They're very
and then
energetically favorable.
a lot of energy is going into that thing, and some of that energy comes out, and it ends up going out frequently the top and the bottom.
Right.
No reference to you and Zoe intended there. And so you have a lot of energy popping out the axes of these things. And as it happens, if you're looking down the axis of a quasar, you have a lot more energy coming at
Right.
you.
It's coming right at you.
Yep.
And so the blazar name, I don't know. These are these things, this is like
I don't know where they even come
people
from.
see something, it's like, what the hell is that?
It's a blazar.
And they give it a name. Same
Yeah.
thing with quasars. Like, what is that? I don't know.
Yeah.
It's a quasi-stellar radio source. That
Obviously.
looks like quasar. And blazar is like, that thing's blazing.
It originally came from, because the category includes BL lac objects, which we'll describe in a second, and optically violently variable quasars.
Oh,
So it's
geez.
a bull quasar.
BL-lac. I think BL-lac is another odd bodily secretion.
It is, yeah. It's
It
a type
could
of,
be.
It's a type of AGN.
Maybe that's why they wanted to sponsor this episode. Huh. I don't know.
We have all sorts of secretions. Blazars are basically secretions from a disk.
So was this single neutrino, the single solitary neutrino,
Yeah.
the coming along the blazar axis of
Yes.
some quasar, which is at the center of some distant galaxy
Right.
with some ridiculous set of letters and numbers as a
Yes.
name?
Yeah. The name has some. And it's just something like 3.7 billion light years away or something like that is this object,
Pretty far.
which is, yeah. And, but it got here.
One little neutrino.
The neutrino made it all the way.
So how many
neutrino-
neutrinos, well, this gets to the answer to your trivia question, the first trivia question, so let's do that, is how many neutrinos pass through per second for us to detect one or something?
Yeah.
What fraction of them do we detect with an ice cube?
I was actually the first trivia question I'd written was, how many neutrinos pass through your body each second?
Yeah, I think I don't know. We've talked about that number before. It's at least in the hundreds. I know.
It's a few.
Yeah.
So it's something like 100 trillion every second.
Pass through
you.
Through me.
Yeah.
What about through me?
Also through you.
Oh.
Slightly fewer, because you have a slightly smaller cross-sectional area.
Okay.
Josh is bigger. But only a little bit.
In all the wrong dimensions. So the first trivia question is, how far on average does neutrino go through ice before it runs into something? And this is related to the question of how many are going through the ice cube thing before interacting with something. And the answers were all 10.
Yeah. 10 meters, 10 kilometers, 10 Earth radii, 10 AU, which is astronomical unit, which is the mean distance from Earth to Sun, or 10 light years.
10 of your Earth radii.
I'm going to go 10 AU. I'm tempted to go 10 light years. I have a feeling that you crafted the question to not have the biggest one be the answer. So I'm going 10 AU.
Okay.
I'm going to go 10 of your Earth radii.
10 of my Earth radii. Yeah, so I knew that you wouldn't go for the extreme because you know how you write tests.
Triple reverse psychologist.
So many reverse
psychology. Reverse psychology.
The answer is 10 light years.
10 light years.
What?
So that as an average neutrino will go 10 light years through a block of ice before it interacts with it just once.
That's a big block of ice.
Yeah. Well, if you said 100 trillion are going through our bodies right now,
every second.
And we only got one
in a second,
in this giant cube.
Yeah. So it's really preposterous. I mean, neutrinos, like I said, they're neutral electrically and very low mass, so they just barely interact with regular stuff at all. And so we'll go through light years and light years of stuff.
Also,
how do they interact with dark matter?
Who knows?
They interact via gravity, and they interact,
not
which is irrelevant on these scales, and they interact via the weak nuclear force, which is a very weak force compared to the strong. Anyway, so it's
well, one of the reasons that people who care about these things care about neutrinos is precisely because of that, because these guys haven't been bothered by anything over those 3.7 billion light years.
Right.
That's how
just
to make it so far so fast.
and gone.
Yeah.
Right.
And they haven't been knocked around left or right, which happens to light.
Right.
You can knock light around. Take a look in the mirror.
Yeah, because light interacts via the electromagnetic force, and so it's very easily perturbed.
The mirror force also.
The mirror force.
I think that's used in a lot of sci-fi.
The mirror force.
The mirror force, yeah.
Yeah, that's what happened to Kirk.
Anything that you say to me bounces off me and sticks on you?
No.
No, that's the mirror force.
Oh, okay, yeah.
Okay, the second trivia.
Which of the following fun astronomy physics things is the shortest time elapsed between a prediction and the prediction of their existence and the confirmation of such?
Will you tell us at the end what that time difference was?
I will.
But you won't tell us before we give our answer?
No.
Is it less than a year?
It is not.
Then I'm going to give you one that I think was less than a year.
Oh, it's going to be a Cassini thing.
It's a planetary thing.
Planetary thing. Yeah.
Oh.
It's maybe not at the level of some of these things. It's not like prediction of a whatever grand
Neptune?
Aspect of stuff. No, volcanoes on Io.
Oh.
They predicted the existence of volcanoes on Io.
The paper predicting volcanoes on Io came out like a month before the discovery.
Oh, that's kind of cool.
Volcanoes.
That sounds suspicious.
That's very sasatisfying because you make a prediction. It's cool if it gets confirmed quickly.
Yeah, well, they were
racing. It can be frustrating if you're waiting lifetimes.
I'm sure there are many, many examples of things like that, because the reason that particular prediction was made and why it was made so close to the actual discovery is Voyager spacecraft was about to fly by Jupiter and get a first close look at Io. So people are like, oh, what are they going to see? Let's do some work. Oh, I think they might see volcanoes because of tidal heating and so forth. So, yeah. So there are a lot of examples like that, but that's one of my favorites. And that prediction was made by the late father of our colleague Robert Peale, Stan Peale, great planetary scientist. Yeah.
Excellent.
All right. So what were our choices?
Your choices were the neutrino, topic of today's discussion, gravitational waves, the Kuiper belt, the top quark, or the bottom quark.
Well, I'm definitely going to say it's not gravitational waves or the Kuiper belt.
Why?
Those were both pretty long.
I think there was I don't know. I just have the feeling many, many years passed between the prediction of those things and the discovery of those things.
I bet you know it roughly for the gravitational waves.
Are you going to count Pluto as the because Pluto's.
I know.
in the Kuiper
By the
Belt,
way, I am the final arbiter of what I'm calling the prediction and what I'm calling the discovery of these things. Even if I don't know much about them, it doesn't matter.
Well, I'm just going to say that Pluto is in the Kuiper Belt.
Right.
And it was discovered before the Kuiper Belt was predicted.
Right, so I'm not counting Pluto as...
Okay.
I'm going to guess beauty.
Because that's a negative time.
Beauty.
Beauty?
I'm going to guess neutrino, since that's the topic of today's podcast.
How do you get this one?
Yes.
Excellent job. It is
high five.
the beauty
High
quirk.
five. Well, I suspected because
Because Jim loves his wife so
Oh,
much.
you just made a trivia question about her. I suspected it's because probably truth was found, and then there was like, oh, there has to be a counterpart, and then it's beauty.
No, it's not that.
Oh.
But... So, wrong logic, but right answer.
Okay.
So, the neutrino was predicted in
a lot.
1930, discovered in 1942, so a dozen years or so there. Gravitational waves, it was 100 years, right? Einstein predicted that in 1916 and it wasn't until 2016.
I remember.
The Kuiper Belt, I'm calling 1930, which was Pluto's discovery.
As the prediction?
Because once they discovered that, people said there should be more things out there. There should be something like that. And it wasn't until 1992.
Yeah. 1992 QB1.
Yeah. That they discovered other objects out there. The truth.
Keep that name.
I was at the DPS meeting in Munich, Germany.
Announced?
When it was announced.
Oh,
that
that's
was
cool.
pretty exciting.
That's
I
awesome.
feel like DPSs would have been way cooler back before like the internet was as big a thing, right?
Yeah.
Because you could like make these big announcements
Right.
at those things. And they still actually do at DPS and AGU do certain days when they do press releases. And they do big releases sometimes associated with those, but I feel like it'd be some of them.
But that was pretty exciting.
Yeah.
Yeah, that's pretty cool. I actually, before I looked it up, and we've talked about it on the program, but I was unaware that it was that recently. I always in my head thought, we've known about this
you're
for
such a young
50
person.
years or whatever.
It's been your whole life, so...
It had, well, I was alive in 1992.
But you weren't a practicing scientist.
I wasn't a practicing scientist. No.
Once something is like, if it existed your whole adulthood, then it's been that way for all time.
Right.
Yeah.
So,
But the truth and beauty quirks were both predicted by a theory in 1973.
Okay.
The reason you would say bottom quark is because which one of those two is the most massive? We've discussed this way before in the podcast.
Top.
Top is more than more. It's the most massive of all the quarks, which means it's going to be the most difficult to detect because you need the most energy, right? High mass means high energy for these particle colliders. So the bottom quark was discovered in 1977. So 4 years from prediction to discovery.
Not too bad.
Whereas it was not till 1995 that the top or truth quark.
And that's one of these things where the prediction drives the search.
Right.
Rather than the one I described of the volcanoes in Iowa where the imminent discovery of something
Right.
motivated predictions.
Yeah. Science works in all kinds of funny ways. I mean, in high school, you learn about the scientific method. It's that we make hypotheses and then we test those hypotheses. But sometimes it works. Yeah, it's a big loop that you can get into at any point. And,
right. Yeah. While you may be thinking this has been the weirdest episode of Star Talk ever, it's actually been a walk about the galaxy.
And best.
Yes. Be sure to like us on Facebook to get all our updates and check out our website at walkaboutthegalaxy.com where you can also see some of our past sponsors with trivia coming soon. Follow us on Twitter
At walk_the_galaxy.
where you can ask us questions and suggest topics that you'd like to hear us discuss. Our theme music was composed by Richard Drusik. Catch up on old episodes wherever you get your podcasts and write us a review by connecting the stars on a star map and post it on our Facebook page.
Aw.
I'm Josh Caldwell.
I'm Addie Dove.
I'm Jim Cooney.
We're the Astroquarks, signing off until the next episode of Walkabout the Galaxy.
Gesundheit.